So in this problem, again, it's a conjugate beam problem, so we're trying to find the slope at point B, which is here, and the displacement. That's funny the way I wrote displacement. The displacement at E, which is the free end. So this would be a long problem, and I don't think it's that instructive to work to the very end, but I did want to draw the shear moment diagram for the real beam, construct the conjugate beam, put the moment on it, and show you how to handle the fact that the moment of inertia for the cantilever sections AB and DE are different than the main span. And at that point, we can just talk about a solution procedure, but we don't have to necessarily go through it. So first things first, let's find the reactions BY and DY. I think I will shortcut this problem a little bit. I think it's pretty easy to see that if you sum moments at D, you can find BY. And then if you sum forces in the Y direction, you would find DY. I think you can also see, because everything is really supersymmetric, that these values are simply just equal to 8 kips. So I'll cut that part out. I'll assume you can manage that. And then we'll go ahead and draw the shear force and bending moment diagram for this problem. So starting with the shear force, positive X, positive shear, all of our values will be in kips. Starting at the left-hand side, and let's work our way through. What kind of shear is this? Yeah, it's going to start off negative. So we're going to start off at -8. There's no load on section 8 from A to B, so there's no change, so I would stay at 8. And of course the slope of the shear diagram is the loading. The loading is 0, so I have a 0 value. And as I move from the left side to the right side, you'll notice that this force of 8 acting up will bring you to 0. So really I have a constant shear of 8 kips over segment AB. Now from B to D, again there's no load, so there's no change in shear, so I'm over here at 0. And now I hit this reaction force up, so that will push me up to 8 kips. Again, there's no load, so there's no change in shear, so it stays 8 kips. And again, the slope is equal to the loading. The loading is 0, so I have a 0 slope. And then that matches my shear at the end. That's kind of an interesting shear diagram. So what's the moment diagram look like? So there's positive X. There's my positive moment. I'll have units of kips and feet. Now starting at the free end, you can see there's no moment at a free end. So I'd have to start here at 0. And there's another free end here, there's no moment there. So I kind of know where I'm going. So the change in moment over the first 10 feet is the area of the shear diagram, which you can see is 8 kips times 10 feet, or minus 80. And the shape of the curve is given by the shear, and the shear is constant and negative. So there's a constant negative slope. The change in moment over the next 20 feet is given by the area of the shear diagram, which is 0. So there is no change, but it stays at minus 80. Again, the slope is 0 because the shear is 0. Then I hit this positive area here. By the way, this was negative. So the change in shear over the last 10 feet is given by the area of the shear diagram. I said moment. I said that wrong. The change in moment over the last 10 feet is given by the area of the shear diagram, which is positive 80, which brings me to 0. The shape of the curve is given by the shear. The shear is constant and positive, so I have a constant positive slope. So there's my moment diagram. Okay? So now I want to construct my conjugate beam and apply this as load. So let's go over here and look at the conjugate beam. Now, if you're already looking ahead, you can probably see that this conjugate beam is not going to be as simple as some of the other ones we worked at. So what's going to happen first is, let's look at the end conditions. So they're both free ends. So on a conjugate beam, they're going to be fixed, right? And these internal pins and rollers are going to become what? Hinges. So I'm going to end up with something that looks like this. Not a very appealing looking structure to deal with. Is it statically determinate? The answer is yes. Well, let's see. I've got 3 unknowns here and 3 there. That's 6 total. That would not be a good place to start with one free body diagram. But I got these 2 hinges I can take it apart. And technically I have 2 more and 2 more. That's what? 10. It seems to be statically indeterminate. However, we're not going to have to worry about a lot of the X forces in here because there's no X loads. So they're all going to be 0. So they're going to be pretty easy to find. So we can find all the bits and pieces we need. Okay? Now I need to apply this as load to that. But remember, I divide this by what? E and I. Now, how can I do that and not have to physically divide by E and I? Well, you can set up kind of a relationship, right? So what does it say right now? It says that the moment of inertia in BD, how is that related to the moment of inertia in AB? It's twice as big. Right? So I do have a relationship between those 2 values. So now I can divide my moment by either one of these. Okay? So what if I now draw a diagram, except I'll call it the moment divided by EIAB. Okay? So when I'm in section AB or DB, that is the moment of inertia. So there should be no change, right? So what should my value be? Let me make just a little sketch here to help keep track of values. You guys follow what I'm talking about?
The moment diagram, right?
This is the moment divided by EIAB diagram, which I'm going to now put as load onto this. So if I'm dividing by the I in AB, well, in section AB, and likewise in section BD, there's no change. But what about here in the middle? If I divide by AB when it's really this, what am I dividing by? It's 2AB. So what's the moment, which is 80, divided by EI 2AB? It becomes half the value. So this would be 80 at minus 80, and that value would be minus 40. Okay, see that? So now I have one constant, but I've adjusted for it. Because the moment of inertia in this middle section is twice as big as the end section, so it got divided by 2. So now I can apply that as load over here, and now my denominator is EI whatever AB is. So when I get to the very end, all my values will be divided by the I of AB or BE, which will be 400. You guys see that? So now I apply this as load to that. So just like we did before, I'm going to first just simply transcribe it. Now in this case, this moment is all negative, and negative means the forces are down. So this is the problem that I would now have to work. And the values here would be 80 kip feet divided by EIAB, and that value would be 40 kip feet divided by EIAB. So I have a common denominator in all my load terms. So that's really what I wanted to show you. Now this particular problem wants the slope at B, which is here, so I need to find what? I need to find the shear here at B. How could you do that? Yeah, I would actually, to find the, I would pull out that section, right? And applied to that middle section is this load, which has the value of 40 kip feet divided by EIAB. And of course, I would have, we're trying to find slope, so it would be shear. So there's the shear at B, positive shear at B. Here's the positive shear at D. And of course, I would also have an axial force, which I'll just call BX and DX. But you can see I don't care about those, do I? And I could easily sum moments about D and find the shear at B. See that? Because all I have to do is turn this into a concentrated equivalent force. Some moments about D, I'll have F1 times its moment arm, the shear at B times its moment arm. I can find the shear at B. That's the slope. Done. The second part of the problem says, what is the displacement at E? E is way over here. So how would I get that? Yeah, you'd have to separate this section here, and I'll draw the moment diagram for that, or the free body diagram for that. And of course, if I can find the shear at B, some forces in the y direction, I can find the shear at D, right? So I would now have the shear at D acting up here, and of course this axial force, which I don't really care much about. Then over here I would have the shear at E and the moment at E. And on that little section, I would have just the triangular force, which has a maximum intensity of 80 kip feet for EIAB. And again, you could find the concentrated equivalent force there, call it F2, and you can find this moment. That moment would be a function of this force and the shear. So it's not as bad as it seems. But I just wanted to walk you through that procedure and not necessarily solve the problem. You can imagine trying to solve this problem with direct integration. Holy cow, that would be a tough one. You'd only have 3 sets of equations, A to B, B to D, D to E, and have 6 constants to solve. You'd be busy for a while. So conjugate beam can take a fairly complicated problem with just point loads. That's just really benefit, and turn it into some relatively simple statics And that's the beauty of it. You know, when this was proposed by Mueller-Breslau or Moore back in the 1850s or 60s, this is all they had was graphical techniques. And they were quite insightful and I guess genius in their view. So any other questions about that? Okay.